So now let's move on to a historical overview of neural networks. So even though neural networks had been around as a concept since the First World War, they really came in fashion with the discovery of the perceptron, which was created by Frank Rosenblatt in 1957. So Rosenblatt proved that using the perceptron, where the perceptron essentially was a neural network without a hidden layer, he could approximate any linear function and he could also perform linear discrimination. So what's linear discrimination? We've discussed about this in previous lectures, but linear discrimination refers to problems where the classes can be separated through only a single line in the space. So you can see some examples of those here. And here you can see an overview of the perceptron, which looks a lot like the example of the artificial neuron we saw earlier. Again, it's essentially a neural network without a hidden layer. However, they soon discovered that the perceptron was useless in solving problems that were not linearly separable. So let's say that you have these toy problems here of using a perceptron in order to simulate logic gates. So you have the AND gate, the OR gate, and the XOR gate. So the AND gate and the OR gate, they're linearly separable. So you can see here the different classes, and it's very easy to draw a line between them in order to separate them. However, the XOR gate requires two lines, so it's not possible to classify using a perceptron. So this was a very important drawback for the perceptron. The reason is that many of the interesting problems that we face in nature, they're actually non-linear, more complicated versions of the XOR problem here. This meant that the perceptron, even though initially it was overhyped, it ended up being pretty much useless for 99% of the problems out there. So this led to the AI winters, among other things. We mentioned AI winters in the past. And then backpropagation was discovered around the 80s, and the area was revitalized a bit. However, most people outside of academia were not very interested because of the issues that had showed up with AI. It had been overhyped, and then the market crashed. So AI and all associated fields had become toxic. However, in the 80s, it became possible to actually train neural networks with hidden layers and solve the XOR problem. So there was some research being done in neural networks, late 80s, early 90s. But then support vector machines came along, which is a nonlinear classifier, which can also separate nonlinear problems through the kernel trick, which has a much better theoretical background. It's much more transparent in terms of what it's doing. And then the most popular approach for doing machine learning until recently was to handcraft lots of features and then train an algorithm to do our work for us. And then we had random forests come out, gradient boosting, graphical models, very powerful models which were applied in many complicated problems quite successfully, and neural networks were kind of forgotten. However, there was an issue with these approaches, that for many domains, handcrafting features is hard. For natural language processing, for example, it can be very time-consuming. For speech recognition, we had all these different techniques, such as framing, Fourier transform, filter banks. And for computer vision, we had all these pre-processing algorithms, complicated algorithms, before we could even pass all those features into a classifier. And then deep learning came along. So Jeff Hinton and other people from his lab managed to train for the first time a neural network with many hidden layers by using a technique of pre-training and then fine-tuning with backpropagation, and they were referring to these neural networks as deep belief networks. So these are the papers which you can also find in the references section, and then they published the work in the NIPS workshop, and they demonstrated that they could get similar performance to the state of the art, but without really having to create all these handcrafted features. So this started steering some interest in deep learning at that time. And since then, deep learning has overtaken everything. And there are many misconceptions around what's really happening. So people are talking about AI coming to take our jobs and steal our freedom. Some people think that we're trying to recreate an artificial brain. Computer scientists think that deep learning engineers essentially just cash up money. Mathematicians think that we have no clue what we're doing because it's more of an experimental science and we're just pushing buttons on a computer to trying to make things work. What I think I do, as this picture says, this is Jan LeCun, one of the most prominent researchers in the field. People in this area believe they're doing cutting-edge research, but in reality, what I actually do most of the time is importing a library in Python and trying out different configurations of a deep learning model until it works. So, what are deep neural nets? So, deep neural nets are simply neural networks with multiple layers. It could be 2, 3, 4, 5, 100, 1,000 layers. It doesn't matter, that's the definition. And they can be used for many things: supervised, unsupervised, and reinforcement learning. Supervised learning being by far the most common scenario. So one of the most important milestones in the history of deep learning was the creation of AlexNet by Alex Krzyzewski, which was a convolutional neural network with rectified linear units and dropout, which is a regularization technique, and it was trained using GPUs, graphical processing units, which made training much, much faster, and they won the ImageNet competition challenge, which is the most important competition for image classification, by a landslide. So this was the start of a revolution. And since then, all you could hear about in computer vision is deep learning. So now deep learning is much easier to do than it was back then. The reason being that we have many good frameworks to do deep learning. So we have, for example, TensorFlow, which is supported by Google, and then we have Keras, which is a wrapper on top of TensorFlow, which can simplify our lives. Then we have PyTorch, which is the equivalent of TensorFlow, but supported by Facebook, and is used more often in academia. It's a bit more complicated, but more flexible. And deep learning, you can see it everywhere, in anything related to computer vision, especially in audio, and complicated problems with big data, you see deep learning. So here is a timeline of the neural networks revolution. Started with the concept of an electronic brain from McCulloch and Pitts in the 40s in the Second World War, then moving on to the perceptron and some other networks. Then people discover that the perceptron is not as useful as people thought because it can't classify nonlinear patterns. So there was this golden age of research for a decade, and then this winter, until we discover backpropagation, people start doing research in neural networks again, SVMs come about, and then in 2010, we have the revitalization of the area of neural networks, and now we are at the peak of this hype. I mean, it's not purely hype because there's lots of substance in it. However, its neural network is like so popular and so hot that people try to apply it in any problem. But it's very, very successful in quite lots of problems, but it remains to see whether it's going to be the single approach that's going to lead us to general artificial intelligence, or whether it's just a very good approach for some particular problems. And also it remains to see how long this progress will keep up and whether we're going to reach a ceiling of performance at some point. So, what are the reasons behind the deep neural network revolution? First of all, storage became cheap as years would go by, and finally we were able to get in our possession very, very, very big datasets and start sharing them with each other. Secondly, we developed better algorithms for training neural networks, such as pre-training and some variants of backpropagation. And finally, graphical processing units became powerful enough to support training deep neural networks, speeding up the training of these networks considerably compared to CPU training. So it looks like deep learning has a way, to a certain extent, to circumvent the curse of dimensionality, as these models are able to digest data of huge dimensionality, but they perform amazingly well. They have superhuman performance in many tasks. So it looks like that for many problems, if you have enough data and powerful hardware, then you can just use a deep neural network and you don't have to be a genius to model this data.